Alright, so let's get started with chapter 4 expressions. C++ provides a rich set of operators and defines what these operators do when applied to operands of built-in type. It allows us to define the meaning of the most of the operators when applied to operands of class type. Okay. This chapter focuses on the operators as defined in the language and applied to operands of built-in type. We will also look at some of the operators defined by the library. Chapter 14 will show you how we can define operators of our own type. Okay. An expression is composed of one or more operands and yields a result when it is evaluated. The simplest form of expression is a single literal or variable. The result of such expression is the value of the variable or literal. Okay. More complicated expressions are formed from an operator and one or more operand. Fundamentals. There are a few fundamental concepts that affect how expressions are evaluated. We start by briefly discussing the concepts that apply to most, if not all, expressions. Subsequent sections will cover these topics in more detail. Okay, so we have basic concept. There are both unary operators and binary operators. Unary operators such as address of and dereference act on one operand. In binary such as equality and multiplication act on two operands. There is also one ternary operator that takes three operands and one operator function call that takes an unlimited number of operands. Some symbols such as asterisk are used as both unary dereference and a binary multiplication operator. The context in which a symbol is used determines whether the symbol represents a unary or binary operator. The uses of such symbol are independent. It can be helpful to think of them as two different symbols. Okay. Then we have grouping operators and operands. Understanding expressions with multiple operators require understanding the precedence and associativity of the operators and may depend on the order of evaluation of the operands. For example, so we divide 10 and multiply 10, 100, 105. Okay. For example, the result of the following expression depends on how the operands are grouped to the operator. The operands to the multiplication could be 10 and 20, or 10 divided by 2, or 15 and 20, right, or 15 and 20 by 2, right. Understanding such expressions is the topic of next section. Okay, operand conversion. As part of evaluating an expression, operands are often converted from one type to another. For example, the binary operator usually expects operand with the same type. These operators can be used on operands with different types so long as the operand can be converted to a common type. Okay, although the rules are somewhat complicated, for the most part conversions happen in unsurprising ways. For example, we can convert an integer to floating point and vice versa, but we cannot convert a pointer to a floating point, right? What may be a bit surprising is that small integral operand, bool, char, short, are generally proportional to a larger integral, typically int. Okay. We'll look in detail at the conversions here. Okay, overloaded operators. The language defines what the operators mean when applied to built-in and compound types. We can also define what most operators mean when applied to a class type. Because such definitions gives an alternative meaning to an existing operator symbol, we refer to them as overloaded operators. Okay, the IO input string and this is output, this is input operators, and the operators we used with string, vectors and other iterators are also overloaded. Okay. When we use an overloaded operator, the meaning of the operator, including the type of its operand and the result, it depends on how the operator is defined. However, the number of operands and the precedence and the associativity of the operator cannot be changed. Okay. This should be in yellow and this should be in blue. L values and R values. Every expression in C++ is either an R value or an L value. These names are inherited from C and originally had a simple mnemonic purpose. L values could stand on the left hand side of an assignment, whereas R values could not. Okay. In C++, the distinction is less simple. In C++, an L value expression yields an object or function. Okay. L value expression yields an object or function. However, some L values such as const object okay. However, some L values such as const objects may not be left-hand operand of an assignment. Moreover, some expressions yield objects but return them as R values, not L values. Roughly speaking, when we use an object as an R value, we use the object's value, its content. When we use an object as an L value, we use the object's identity, its location and memory. Okay, got it. Operators differ as to whether they require an L value or R value operands and as to whether they return L values or R values. The important point is that with one exception that we'll cover here, we can use an L value when an R value is required, but we cannot use an R value when an L value location is required. When we use an L value in place of an R value, okay, the object's content, its value are used. We have already used several operators that involve L values. Assignment requires a non-const value. Assignment requires a non-const L value as its left operand, right, and yields its left hand operand as an L value. Okay, assignment operator requires a non-const L value as its left hand operand and yields its left hand operand as an L value. The address of operator requires an L value operand and return the pointer. Okay, right. Return the pointer. The built-in dereference and subscript operator and the iterator dereference in string and vector subscript operator all yield L values. Okay, so they give us a location. The built-in and iterator increment, the built-in and iterator increment and decrement operator require L value and prefix and also yields an L value. Okay. Now because it still gives us the object. As we present the operators, we will note whether an operand must be an L value and whether the operator returns an L value. Okay. So address of operator returns a R value. Okay. Address of. Right. This is an R value. Okay. As we present the operators, we will note whether an operand must be an L value and whether the operator returns an L value. L values and R values also differ when used with declare type. When we apply declare type to an expression other than a variable, the result is a reference type. The expression yields an it's an L value. Okay, so if it an object, it is a reference. As an example, assume P is a int pointer because dereference yields an L value. Declare type is int. On the other hand, because the address of operator yields an R value. Okay. uh, the pointer to a okay. Precedence and associativity. Okay, an expression with two or more operators is a compound expression. Right. That is easy. Evaluating a compound expression involves grouping the operands to the operator. Precedence and associativity determines how the operators are grouped. That is, they determine which part of the expression are the operands for each of the operator. The programmers can override these results by parenthesizing the compound expression to force a particular grouping. In general, the value of an expression depends. In general, the value of an expression depends on how the sub-expressions are grouped. Operands of okay. Hmm. in, in general, the value of an expression depends on how the sub-expressions are grouped. Operands of operators with higher precedence group more tightly than operands of operator with lower precedence. Okay. Associativity determines how to group operands with the same precedence. Okay. For example, multiplication and division have the same precedence as each other, but they have a higher precedence than addition. Therefore, operands to multiplication and division group before operands to subtraction. The arithmetic operators are left associative. The same precedence group left to right. Because of precedence, this is 23. Because of associativity, this is 15 minus 3 is 12. 12 minus is 2. Oh, left to right. Sorry. Left to right. Okay. Left to right. Okay. As a more complicated example, left to right evaluation of the following expression yields 20. Okay. So we'll okay, so these are done left to right. So we have 12. 12 divided by 2 is 6. Then we go 6 plus 6. Oh. These are okay. So left to right, right. 6 plus 6, 12. 12 plus 2, 14. Yields 20. How is it yielding 20? We are going from left to right. Left to right evaluation. As a more complicated example, our left to right evaluation of the following expression yields 20. This is 4, 2, 6. Huh. Other imaginable is this. Result includes 9, 14. In C++, the result is 14. Yeah, because this expression. Huh. That's what I thought. It should be 14. Okay. In C++, the result is 14 because this expression is equivalent to this. Parentheses override precedence and associativity. Okay. we can override the normal grouping with parentheses. Parenthesized Parenthesized expressions are evaluated by treating each parenthesized expression as a unit and otherwise applying the normal precedence rule. Okay. For example, we can parenthesize the expression above to force the result to be any of the four possible values. Okay. When precedence and associativity matters. We have already seen examples where precedence affects the correctness of our programs. For example, consider this. In expression, now this would return a point 0 plus 4, this would return 4. Plus 4, this is 8. Okay. We have already seen examples where precedence affects the correctness of our programs. For example, consider the discussion here about the reference pointer arithmetic. Okay. If you want to access the element at location ia plus 4, then the parentheses around the addition are essential. Without parentheses, I is grouped first and 4 is added to the value and return then R value, right? Okay. The most common case that we have seen in which associativity matters is in input and output expressions. As we'll see, the operators used for I/O are left associative. Okay, so they are evaluated from left to right. This associativity means we can combine several I/O operations in a single expression. Okay, so it reads, then gives the left hand operand Cn, there's Cn, right, reads. Okay, table 1412 lists all the operator organized into segments separated by double line. Operators in each segment have the same precedence and have higher precedence than operators in subsequent sequence. For example, prefix, for example, the table 1412. For example, the prefix increment and dereference operators share the same precedence, which is higher than that of arithmetic operators. The table includes a page reference to each operator's description. We have seen some of the operators already and will cover most of the rest in this chapter. However, there are few operators that we will not cover until later. Then we have what is the value returned by this. Okay. So we go left to right, they're same. So we'll evaluate this. This is 200 divided by 2 is 100, 105. Okay. So using table 1412, parenthesize the following expression to indicate the order Okay, so using table 1412, parenthesize the following expression to indicate the order in which operands are grouped. Operands, yeah. Correct, this has more precedence over this, so this will be grouped first. Similarly here. Okay, order of evaluation. Precedence specifies how the operands are grouped. It says nothing about the order in which the operands are evaluated. In most cases, the order is largely unspecified. Okay. In the following expression, we know that f1 and f2 must be called. Okay, we know that f1 and f2 must be called before the multiplication can be done. After all, it is their result that are multiplied. However, we have no way of knowing whether f1 will be called before f2 or vice versa. Okay. For operators that do not specify evaluation order, it is an error for an expression to refer and to change the same object. Hmm. Expressions that do not have undefined expressions that do not expressions that do so have undefined behavior. As an example, for operator that do not specify evaluation order, it is an error for an expression sign to refer to and change the same object. Expressions that do so have undefined behavior. Okay. As a simple example, the say, what is this input the output stream operator makes no guarantee about when or how its operands are evaluated. As a result, the following output expression is undefined. Okay, because this program is undefined, we cannot draw any conclusions about how it might behave. The compiler might evaluate plus plus I before evaluating I, in which case the output will be 1 1. Okay, or the compiler might evaluate I first, in which case the output will be 0 1, or the compiler might do something else entirely because this expression is undefined behavior. The program is an error regardless of what the code compiler generates. There are 4 operators that do guarantee an order, the order in which operands are evaluated. We saw in theory the logical left to right, left hand and operator guarantees that its left hand operator is evaluated first. Moreover, we are also guaranteed that the right hand operand is evaluated only if the left hand operator is true. The only other operator that guarantees the order in which operands are evaluated are logical OR, the conditional operator, and the comma operator. Okay. Now, order of evaluation, precedence, and associativity. Order of operand evaluation. Okay, order of operand evaluation is independent of precedence and associativity in an expression. Okay. So order of operand evaluation is independent of precedence and associativity. Expressions such as this: precedence guarantees that the result of G and H are multiplied. Associativity guarantees that the result of F is added to product of G and H, and that the result of that addition is added to the value of this. Okay. And for same precedence left to right. There are no guarantees as to the order in which functions are called. If f, g, h are independent functions that do not affect the state of the same object or perform I/O, then the order in which the functions are called is irrelevant. If any of these functions do affect the same object, then the expression is an error and has undefined behavior. Okay. Exercise 4.3. Order of evaluation for most of the binary operator is left undefined. Okay, is left undefined to give the compiler opportunities for optimization. This strategy presents a trade-off between efficient code generation and potential pitfalls in use of the language by the programmer. Do you consider that an acceptable trade-off? Why or why not? I don't think it's a good trade-off. Since the programmer may forget about these rules and execute which works on one compiler while doesn't on other. Right? Order of evaluation for most of the binary operators is left undefined to give the compiler opportunities for optimization. This strategy presents a trade-off between efficient code generation and potential pitfalls in the use of language by the programmer. Do you do you consider that an acceptable? I don't think it's a good trade-off since most of the programmers may forget about these rules and use different behavior, which works in compiler while it doesn't on another. Okay, managing compound expressions. When you write compound expressions, two rules of thumb can be helpful. When in doubt, parenthesize expressions to force the grouping that the logic of your program requires. If you change the value, okay, let's ask okay, order of evaluation is often undefined in languages. Is it a languages for compiler optimization? Is it a good trade-off? Okay, so I'm aware that standard implementation may choose in which order arguments of a function are evaluated. But are there any implementations that actually take advantage of this scenario where it would actually affect my program? But I'm not looking for someone to tell me that the order of evaluation can't be relied on. I'm looking at that. I'm only interested in whether a compiler actually do evaluate out of a left to right order, because my guess would be that if they did, lots of poorly written code would break rightly. So, but they would still probably complain. It depends on the argument type, the functions calling convention, the architecture, and the compiler. On x86, the Pascal calling convention evaluates argument left to right, whereas in the C calling convention, it is right to left. Most programs which run on multiple platforms to take into account the calling convention list of surprises. This is an article. We also want to take a look at the stack calling convention. And okay, so long as we are splitting here, my answer treats this not as language question but as a platform one. Language standard does not guarantee or prefer one over the other and leaves it as unspecified. Note the wording, it does not say this is undefined. Unspecified in this sense means you cannot count on non-portable behavior. I don't have C spec draft handy, but it should be familiar to that from my C++. That is undefined. Rely on unspecified behavior, not undefined, unspecified, which works on one. Then we have, okay, if you change the value of an operand, don't use that operand elsewhere in the same expression. Okay. An important exception to the second rule occurs when the sub-expression that changes its operand is itself the operand to another sub-expression. For example, so we increment. Okay, so we dereference first and change it. The increment changes the value of item. Now the changed value of an iter is the operand to the dereference operator. Okay, where is 1, 2 table 412. Where is table? Can I see table 442? Can we take a look at table 412? Where is table 412? Let me see table 412. Is this table 4.3 bitwise? No. Alright. Unary plus, unary minus plus plus. Okay, where was it referencing in the table? 4 into page 160. This is page number 1. Okay, move to page 166. Come back to 139. Okay, so we have, okay, so postfix, these are associativity, and okay, so postfix, prefix. Okay, postfix increment has higher works on L value, higher precedence than the dereference operator. Okay. Okay, they all have the same precedence. Postfix, type ID, explicit cast, and it has the same precedence, and using associativity, it is evaluated left to right. Okay, got it. My man. Alright, here we go. Okay, the increment sub-expression must be evaluated before the dereference can be evaluated. Such uses poses no problem. Okay. Then we have arithmetic operators. These are arithmetic operators, left associative, so they have more precedence, unary plus and minus. Okay. Table 4.1, the operator tables in subsequent section groups the operators by their precedence. The unary arithmetic operators have higher precedence than the multiplication and division operators, which in turn have higher precedence than binary addition and subtraction operators. Operators of higher precedence group more tightly than two operators with lower precedence. These operators are all left associative, meaning that they group left to right when precedences are all the same. Okay. Unless noted otherwise, the arithmetic operators may be applied to any of the arithmetic types, or to any type that can be converted to an arithmetic type. Okay, the operands and results of these operators are the operands and results of these operators are R values as described here. Operands of small integral types are promoted. Okay, of course, when you give R expression, when expression is evaluated, it will give an R value as expressed in operands as described in here. Operands of small integral types are promoted to a larger integral types, and all operands may be converted to a common type as part of evaluating operator. The unary plus the unary plus operator in addition subtraction may also be applied to pointers. Covered the use of binary with the unary plus operator and the addition And subtraction operator may also be applied to pointers. Yeah, we know that. Okay. Covered use of binary pointer operands. When applied to a pointer or arithmetic value, unary plus returns a possibly copy of the value of its unary plus. The unary minus operator returns the result of negating the possibly promoted copy of that value of its operand. Okay. So we have minus true, B is still true, negative. Okay. So we noted that in pool, that pool value should not be used for computation. The result of negative p is a good example of what we had in mind. For most operators, operands of type bool are promoted to int. Okay. In this case, the value of b is true, which promotes to the int value 1. That value is negated, yielding minus 1. The value minus 1 is converted back to bool and used to initialize p2. This initializer is a non-zero value, which when converted to bool is true, thus b2 is true. Okay. So overflow and other arithmetic exceptions. Some arithmetic expressions yield undefined results. Some of these undefined expressions are due to the nature of mathematics, for example division by 0. Others are defined due to nature of computer, for example due to overflow. Overflow can happen when a value is computed that is outside the range of values that the type can represent. Consider a machine which stores shorts on 16 bits bytes. In that case, the maximum is 2 raised by 16 minus 1. On such a machine, the following compound expression overflows. Okay, short value is this calculation overflows. The assignment to short value is undefined, representing the signed value of this requires 17 bits, but only 16 are available. On many systems, there is no compile time or runtime warning when an overflow occurs. As with any undefined behavior that happens, what happens is unpredictable. On our system, the program completes and writes this. Okay, the value wrapped around the sign bit, which had been 0, was set to 1, resulting in a negative value. On other systems, the result might be different or the program might behave differently, including crashing entirely. Okay. Okay. So when applied to objects of arithmetic type, the arithmetic plus, minus, multiply and divide have their obvious meanings: addition, subtraction, multiplication and division. Division between integers results an integer. Okay. If the quotient contains fractional part, it is truncated to 0. This is 3, 18, this is 3, no remainder. The mod operator, known as the remainder or the modulus operator, computes the remainder, that the result from dividing the left hand operand by the right hand operand. The operand to mod must have integral types. Okay. So we cannot find modulus on floating types. In division, a non-zero quotient. Okay. In division, a non-zero quotient is positive if the operands have, okay, in a division, a non-zero quotient is positive if the operators have the same sign, and negative otherwise. Okay. Earlier versions of the language permitted a negative quotient to be rounded up or down. The new standard requires the quotient to be rounded to 0, that is truncated. Okay. For non-zero, it will be positive. Okay. Negative. Okay, so we can't have a negative quotient. Same sign. If the operands have the same sign or negative. Okay, we can have a negative in a division. A non-zero quotient. A non-zero quotient is positive. A non-zero quotient is positive if the operands have the same sign negative otherwise. Okay, earlier versions of the language permitted a negative quotient to be rounded up or down. The new standard requires the quotient to be rounded towards 0. Okay, I don't get this, but we'll see. So the modulus operator is defined. The modulus operator is defined so that if m and n are integers and n is non-zero, then m by n into 10 plus m mod n is equal to m. By implication, if m mod n is non-zero, it has the same sign as m. Earlier versions of the language permitted to have same sign as the n or implementations. Is equals to m. Okay, so we can find this. And this is negative of m divided by n times n. Okay. By implication, if f mod n is 0, it has the same size as m. Earlier versions of the language permitted m mod n to have the same sign as n, or implementation in which negative was rounded away from 0, but such implementations are now prohibited. Moreover, except for the obscure case where minus m overflows, minus m divided by n and m divided are always equal to this. Okay. Observe guys, when minus 1 overflows, minus m over n or m divided by n are always equals to this. Okay. And then m mod minus n is equal to m mod n and minus m mod. Okay. So we can say more correctly, okay, this is 3, right, and division is also 3. This mod is 0, okay, division is 3. Okay, both have negative signs. Okay, so this is because, see, m mod negative n was nothing and minus n, so this disappears and a single negative sign remains. Okay, that's 2 minus 8 minus, okay, so these are rounded away from 0. So it is 1, right, plus minus 4. Okay, got it. Okay, parenthesize the following expression to show how it's evaluated. Test your answer by compiling the expression. Okay, so first of all, we'll go with all the multiplications, and these are evaluated first. So we'll go with this, okay. So this, then this will be evaluated first. 12 divided by 3 is 4, 4 into 4 is 16. Then this will be evaluated, and this, then this whole divided. We'll go from left to right. So we will have 4 into 16 plus 75 plus 0 divided by 2 is 0. 16 plus 75 is 1191. Okay, so this should result in 21. This is exercise equals 91. So exercise 4.2. Right. Okay. 4.2. This okay. Exercise. Okay, exercise. So exercises. Okay, how did I went to exercises. Exercise. Okay. Exercises 4.2. We go here. 4.2.cpp. Right. 4.4. 4.4 CPP. Movement apps. Stream. Main. I want to evaluate. Equals 12 divided by 3. 12 divided by 3 times 4. Give plus 5 times 15 plus 5. 5 times 15. Then we have 24 mod plus 24 mod 4 divided by 2. Okay. See. Right. Okay. So that is correct. Alright. So then we have determined the result of the following expression. We multiply these minus 90 plus the quotient will be 4. So minus 90 plus 4 is minus 86. 5 for the 20. Right. Then we have 30 divided by 3 is 10. 10 times 21 is 210. This should be 0. And we have, okay, 21 times 3 is 63. 63 divided by 5 is 12. 63 12. 12 minus 30 is minus 18. Okay, so this will be minus 10 times 21 is minus 210, and then minus 210 mod 4, it will be negative of 210. 4 5s are 20. 1 10 to the 8 2. So this should be minus 2. This will be negative m mod n equals negative of m mod n. Okay, so let's check each of these answers. 4.5. Look into x and p equals minus 30 times 3 minus 30 times 3 plus 21 times 5 plus 21 divided by 5. I don't want to buy, please. Then we have minus 30 plus 3 times 21 by 5. Yes. Minus 30 times 3. 30 times 3 plus 30 plus 3. Okay. 30 plus 3 then times 21 times 21 divided by 5. PQR goes 30 divided by 3. Okay, so 30 divided by 3. 30 divided by 3 times 21 mod 5. Okay. So 30 divided by 3 times 21 mod 5. Okay. Then we have minus 30 divided by 3. Minus 30 divided by 3 times 21 mod 4 times 21 mod 4. See? Minus 86, minus 18, minus 86, minus 18, 0 and negative 2. Okay, great. What does overflow mean? Show 3 expressions that will overflow. Okay. So, right. Overflow is when the value of the evaluated expression cannot be stored within its L value as there is no space as that result of the expression is out of the range of the L value. Okay. So I'll continue this next time.